Welcome, calculus students, to the third part of our section 4.3 in our textbook, which is a rather long section. And this part is focusing on what's called the trapezoid rule, or the trapezoidal rule. And what is the trapezoid rule? It's just yet another way to approximate the value for what we call a definite integral. So just a really quick reminder of what a definite integral is. It's an expression that looks like this. You have your long, stretchy s, we call it the integral sign. And it has a lower limit of integration and an upper limit of integration. So you have number values here. You've got your function on the inside and then dx. So what is the value of this definite integral representing? The value of this definite integral represents the area under that curve, right under f of x, but above the x-axis and then in between these endpoints of a and b. So it equals the value of this shaded area here, which as we have talked about is a difficult area to find given this curvy top up here. So the trapezoid rule is another way of, it doesn't find the exact value, but it finds an approximate value for that definite integral. And the formula given for it in your textbook looks like this here. So it has the b minus a over 2n times the quantity of this long expression, f of x sub naught, or x sub 0. This is considered to be your left endpoint. This is like the a value up here. It's this guy right there. And then these, f of x sub 1, f of x sub 2, f of x sub n minus 1, these would be the y values evaluated at each in-between endpoint of your subintervals, which we'll talk about in a second. And then this f of x sub n would be like your final right endpoint. It'd be like your b value, basically, from your definite integral. So it'd be this guy right up there. Now, how did this formula come to be? Well, I kind of want to go through with you the process of how we derive this rule so that you understand what it's actually doing, and as a result, don't necessarily need to memorize this formula. But also because sometimes you're asked to use a trapezoid rule where this formula wouldn't necessarily work, which I'll explain why later. So let's just take a moment right now to figure out where this rule came from and how it's helping us approximate this area under a curve. All right, so to derive the rule, we're going to first take, for example, the graph of this curve f of x, and imagine that we want to find the area under the curve, but above the x-axis from these points A and B. So what we typically do, or what we have been doing up till now, is taking that larger area and slicing it into smaller subintervals to find areas of smaller shapes. Now, remember, we can slice this into however many intervals we want. In this case, in this example, I'm going to use 4. Now, what we've been doing up till now is using rectangles, rectangular approximations. We've been finding the areas of these rectangles and adding them up to get an approximate value of the area under that curve. Of course, we've been, in this case, I have 4, but we could add in more if we wanted to get less error, right, under the curve and have a more accurate answer. Or we can use trapezoids, because if you look at the difference between a rectangle under the curve and a trapezoid under the curve, you can see that by allowing the top of these shapes to be diagonal versus horizontal, it cuts back on a lot of that error that we saw under the curve. There still is some error, right? It's not going to get the exact value, but just by using these trapezoids versus rectangles, we can actually cut down on a lot of the error caused from using these straight edged shapes versus curvy shapes. So we're going to do a similar method, though. We're just basically going to find the areas of these different trapezoids and add them up, just like we were doing with rectangles. To do that, though, we're going to need to use the area formula for a trapezoid. So we kind of have to go back to geometry here and remember that the area of a trapezoid is equal to 1/2 times the sum of these two bases, base 1 plus base 2 times the height. So what are these values coming from? Well, first of all, the height for each trapezoid is going to end up going along the x-axis. So let's see why that is. So it can, again, thinking in geometry terms, we think of trapezoid shapes that look something like this. We've got these two parallel sides. We've got a vertical distance between them, which we're referring to as the height. That's what this h is referring to over here. And then, of course, this slanted side. Now, usually my bases run horizontal and my height runs vertical for a trapezoid when we think of it in geometric terms. So it's the same shape, but what we're going to do to put them under the curve is kind of flip them on their side so that the slanted part goes along the curve. right? It could slant up or it could slant down depending on how I place the trapezoid. But the idea is we're kind of turning them over to their side. So now these heights, what used to be the vertical distance, is now this horizontal distance between each of the x values in our subintervals. Additionally, these parallel sides that each trapezoid have, which normally were bases, right? Normally they were thought of as like these horizontal, lengths. Well, because we're flipping them sideways, those quote bases are now these vertical heights right here, going from the x-axis to the curve. So they're basically the values of f of x evaluated at each of these different x values of your subintervals. So looking at this graph above, right, with my 4 trapezoids, the heights would be the changes in x between each of these little x values, these in-between endpoints of my subintervals. So how do I find that length? Well, first of all, it would be the same length between all intervals, because what I would do is I would take this entire length from a to b. I do that by subtracting. B minus a finds the entire length between a and b. And then if you divide it by n, your n, of course, is referring to the number of trapezoids or the number of intervals. You're basically saying, hey, take this length and split it into n equal widths. N in this case is 4. Split it into 4 equal widths. And so that's how we find our delta x, which is basically our height for these trapezoids. Secondly, to find the values of your bases, right, because we have to do base 1 plus base 2, we take these x values at each of these endpoints of your subintervals. We plug it into the function to figure out how high it would go, right, to figure out where the y values are, which are vertical distances. So that's giving me these lengths, these vertical lengths, which are basically my bases for each trapezoid. So knowing that, we just basically have to use all that to find the area of each trapezoid and then add it up. So let's start with this first trapezoid here. This first trapezoid had endpoints of a, which was my left endpoint, and then x sub 1, my first in-between x point. So I have 1/2 base 1 plus base 2 times height. Again, height is this delta x here, the b minus a over n. F of a would be my base 1 because it's my vertical distance up between the x-axis and the curve where x is a. So it's f of a, right? That's my base 1, and then base 2 would be f of x sub 1. So this is the first area of the first trapezoid. Okay, got that one. Now I got to find the second area of the second trapezoid. So same thing, 1/2 base 1 plus base 2 times height, which is the delta x. Now the f of x1, we had used that before. That was base 2 for my first trapezoid. Notice I need that same y value to use as base 1 for my second trapezoid. It's like a parallel side. It's being used for 2 different trapezoids. So that's base 1 of my second trapezoid, and then f of x2 would be base 2 of my second trapezoid. So got that one down. Then next I got to find my third one. Hope you can see that. It's kind of a bright yellow, but it's same thing, 1/2 base 1 plus base 2 times height, where base 1 would be f of x sub 2, using that one again, because that's another bordering side. I can use it for 2 trapezoids, plus f of x sub 3 is my base 2 for this trapezoid, and then times height, which is my delta x. Got those 3, and then I just have to get that last one, which is 1/2 base 1 plus base 2 times height. And you can see again, I've got my f of x sub 3. That's my base 1 for the last trapezoid. It was base 2 for the third one. It's base 1 for the last one. Plus f of my final endpoint, right, which was base 2 of my final trapezoid, and then times the height, which was the delta x. So basically, I just find the 4 areas of these 4 trapezoids, and then I just have to simply add them up. So when I do that, I get this. Now what I noticed was each of these areas had a 1/2 in common, so I can just kind of factor that out. And because of the way we determined the height, which was we took this length and divided it into n equal parts, then I know that that value will also be the same for each of these, so we can factor that out as well. And then I just have all of my different y values at all of these different, evaluated at these different x endpoints. And I notice that I have 2 y values at each of my in-between x values because those were being used, like each of those sides were being used twice because they were bordering on other trapezoids. Okay, so that basically gives us this, which if I combine like terms, ends up equaling this expression here. So notice that all the in-between y values end up doubling up because they were used twice as a base 1 for one trapezoid, as a base 2 for the other one. And the endpoints were only used one time. I only had to plug those into the function one time to use as base 1 for the first trapezoid and then base 2 for the final trapezoid. And then I have common values of 1/2 and h. So notice this was an example where I had 4 trapezoids, okay? And by the way, when you have 4 trapezoids or 4 intervals, then you would need 5 endpoints. Notice I have 1, 2, 3, 4, 5. The left endpoint, the right endpoint, and the 3 in-between points. So however many intervals you have, you're going to have 1 additional endpoint. If I were to have 5 trapezoids, then I would need 6 endpoints. If I were to have 6 trapezoids, I would need 7 endpoints. So remember, you always have 1 extra endpoint in addition to however many shapes you have or however many subintervals you have. But this again was just a generic example. What I want to do is generalize this for any number of partitions, not just 4. So allowing n to be any number of partitions. That's how you get this formula here, which you can see is beginning to match that formula on your handout a lot more. So I just kind of multiplied the 1/2 times the h and got h over 2. This is my f evaluated at my first endpoint, plus 2 times each of the y values evaluated at each of those in between x values, and then plus a final y value evaluated at my final right endpoint. And again, this h here is referring to the delta x, the change in each x value, which was determined using this formula, b minus a divided by n. And again, just want to point out one more time that each of those in-between y values gets doubled, while the left and the right y values do not. So let's now take this formula that we can see that we found by simply finding areas of trapezoids and adding them up, and compare it to the definition we see in our textbook. Okay, so this was the area that we had derived using just the sums of areas of distinct trapezoids being added up. So what I wanted to point out is that your textbook calls this a value x sub 0 to indicate like the first x value or the very first endpoint. And then it refers to b, which is your far right endpoint, as x sub n, which is kind of thought of as the nth endpoint, right? X sub n. So it's like the very last one. So it's our b, our right endpoint. And then h is just the change in x, right? It's the distance between all of those in-between x values along the x-axis. So we had found that by taking the full distance between b and a, dividing it by however many subintervals or trapezoids we were going to use. So if you kind of put that all together, right, you let h equal b minus a over n, you let a be called x sub 0, and you let b be called x sub n, what you end up with is this. B minus a over n divided by 2 times the quantity f of x sub 0 plus 2 times f of all my in-between x values, all the way up until my second to last y value, and all the way up until my last one. If we let b be referred to as x sub n, right, my very final endpoint, then I get this. And then b minus a over n divided by 2, that can be simplified to equal b minus a over 2n. So that's how our textbook got that. It was just the height being determined by b minus a over n divided by 2. When simplified, just becomes b minus a over 2n. And then these were all of my different bases, right? Base 1 plus base 2, except that base 2 was also used as base 1 for the next trapezoid, so it was used twice. This one is used as base 2 for the second trapezoid and base 1 for the third, and so on and so forth. So our in-between y values get doubled, and our far left and far right y values are only used once. This was base 1, so to speak, of the very first trapezoid, and since it wasn't bordering any other trapezoids, it's used once. And then this was base 2, so to speak, of our very last trapezoid, our nth trapezoid. And so it was only used once because it wasn't bordering any other trapezoids. And then these were all used twice since they were each a base 1 and a base 2 for bordering trapezoids. So that is essentially where the rule comes from. So now let's look at a couple examples of how we use that rule. Okay, so here in example 1, it wants us to use a trapezoid rule to approximate the value for this definite integral right here, which is missing the dx. I'll add that in there. And it says it wants us to use 4 trapezoids or 4 subintervals. Okay, so what I'm going to do, so first of all, what is this? What is this? This is the area under the curve, right? Under this curve between 0 and 2. So below the curve, above the x-axis, between 0 and 2. So it's like this area in here. But we're going to split it into 4 trapezoids. So I need to cut up this length from 0 to 2 into 4 equal parts. So let me do that first. So my height, right, of each trapezoid, or my delta x, is going to be b minus a divided by n. So a in this case is 0, b in this case is 2, right? My left endpoint, my right endpoint. So I'm going to do 2 minus 0 divided by my number of trapezoids, which is 4. So I can see that each of them will have a thickness or a width of 1/2. So my first trapezoid will end at 1/2. Second one will end at 1. The third one will end at 1.5. And the fourth one will end at 2. And so there's my 4 trapezoids there with their diagonal tops there. Okay, so what I'm going to do is I'll use that formula. So our book basically says to do b minus a divided by 2n, which, by the way, is just 1/2 times the height. So just remember that. So once you find your height, which is 1/2, it's going to just be 1/2 times that. But anyway, I'll use the formula here. So b minus a over 2n times the quantity f of my very left endpoint, which in this case is 0, plus 2 times f of my first in-between endpoint. So f of 1/2. Maybe I'll call it 0.5. Plus 2 of my second, or 2 times y evaluated at my second intermediate x value, plus 2 times my third, the y value evaluated at my third intermediate x value, and then plus 1, just 1 of the y values evaluated at the final endpoint. So I had to multiply all the in-between ones by 2. Now this b minus a over 2 we already found to be 1/2, but maybe I'll just kind of plug that in here so you can see how that works. Where n, of course, is the number of trapezoids, which is 4. So you can see I'd end up with 2 over 8, which reduces to 1/4, which is the same thing as this height. So each trapezoid has a height, right, a change in x of 1/2 divided by 2. And that comes from the area of a trapezoid formula, which is 1/2 base 1 plus base 2 times height. This, of course, is the height for every trapezoid. You divide that by 2 or you multiply by 1/2, you get 1/4. But I can also find that using the formula from our textbook. Okay, so that 1/4 is going to be multiplied by f of 0. So f of 0 is what I get when I plug 0 into this equation here, the equation for my curve, which is x squared. F of x is equal to x squared. It's the equation here in my definite integral, and I'm going to evaluate that at 0. So this will be 0 squared plus 2 times 0.5 squared plus 2 times 1 squared plus 2 times 1.5 squared plus just 2 squared. I don't multiply that by 2 because it's the last endpoint. You only multiply the in-between y values by 2 because they are used as bases for 2 trapezoids, right? This is used as base 1 for my first trapezoid, and then, or sorry, base 2 for my first trapezoid, and then used again as base 1 for my second trapezoid. This guy is used as base 2 for that second trapezoid, but base 1 for the third trapezoid. This guy, the 1.5, is used as base 2 for the third trapezoid, and base 1 for the final trapezoid. So all those in-between y values are all bordering sides of bordering trapezoids, but the left side and the right side are not, so they're used only once. By the way, you can see here this is a height of 0 because this first trapezoid is actually a triangle. So anyway, that's how that worked out. So then I just evaluate all of this and multiply it by 1/4. So that'd be 0 plus 2 times 0.25 plus 2 times 2.25 plus 4. So this here would end up being 0.5. That here would end up being 4.5. And so I just need to add all that up and divide it by 4. So I end up having to do 1/4 times 11, or 11 divided by 4, which ends up equaling 2.75, we'll just say units squared. So this is my approximation for the area under the graph of y equals x squared, but above the x-axis between 0 and 2. So it's my approximation of that area there. Now, of course, I know there's still a little bit of error because this is curved, whereas the trapezoid edges, right, are straight. So there's still a little bit of error there. So what I want you guys to do is also compare your result with the exact value that you can find using, well, we will eventually teach you how to find it, but until then, you can find it on your calculator and then compare with this. So why don't we take a moment to do that right now? So I wanted to give you guys a quick run through of how you would find the value of a definite integral on your calculator so that you can check your answers. So it involves using this math feature right here. If you click math, there's some different things you can do. But if you scroll down using your arrow keys, what we're going to use is option number 9, FNINT. You can either arrow down to 9 and hit enter, and it'll give you this definite integral notation. Or if you hit math, you can just hit the number 9. So knowing that it is option 9, you can just hit 9 and it'll bring you here. So I'm just going to use the one we just did as a way to check. So we were doing the integral from 0 to 2. So you type in your a and b values. So my left endpoint and my right endpoint. And the function that I was looking for the area under was x squared. So this is the button you always hit for your variable. And then I'm going to square it. And then this is where you type in your variable of integration, which in this case was x. So we were taking the integral from 0 to 2 of x squared with respect to x. Of course, we approximated using a trapezoid rule. And what this will give you here is the exact value of the area. So I hit enter, and then I get my 2.6 repeating that I had shown you earlier. So this is our exact value here, helping us see that our approximation was on the right track. So that value that we found on our calculator for the definite integral was about 2.6 repeating, or was exactly 2.6 repeating, or 2 2/3. So we can see that our estimate was an over estimate. And it's important that we know how to tell whether your trapezoid rule is an over or underestimate, and it has to do with the concavity. So notice that this graph was concave up, right? It was opening up, and so what happens is, I'm just going to draw an exaggerated picture. This is a concave up curve. If you draw a trapezoid, right, to try to, if you connect those endpoints using a trapezoid of a curve that's concave up, imagine I'm zooming in, of course, then you can see that your trapezoid edge being straight is going to be above the top of your curve if your curve is concaving up, meaning there's going to be this additional area that the trapezoids are finding that aren't actually under the curve. So when you are looking at a concave up curve, then your trapezoid rule will be an overestimate. And then, of course, the reverse is true. If your curve is concave down, then your trapezoid rule will be an underestimate. So this is also important for us to know. And I can think of I could draw an exaggerated picture for that as well. Maybe I'll do that down here. So if you have a curve concaving down, okay, again, imagine I'm zooming in on a curve, and I'm drawing a trapezoid between those endpoints. Because I have to draw the top of the trapezoid as a straight diagonal line, it would have to lie below a concave down curve. So then there would be this area under the curve that I didn't account for with my trapezoid. So my trapezoid area would fall a little short. It would be an underestimate. Okay, now I'd like you guys to try one and pause your video, see if you can get the correct approximation using the trapezoid rule here, and then come back and check your answer. Okay, so the approximation that you should have found using the trapezoid rule with 6 trapezoids to approximate the value of this definite integral, which again is missing a dx, should have come out to have been about 7.908107915. So basically we start by finding what the width of each of my trapezoids would be, which would be the height, or the delta x, which is b minus a divided by n. Or 6 minus 0 divided by 6, which is 1. So each trapezoid has a length of 1. So that helps me figure out like what my different x endpoints should be, which basically are just counting by 1. 0, 1, 2, 3, 4, 5, 6. Notice that since I have 6 trapezoids, I have 7 endpoints. 1, 2, 3, 4, 5, 6, 7. Okay. Then my trapezoid rule says to basically plug in the following information. B minus a over 2n times each of the y values evaluated at each of my x endpoints of my subintervals, where the in-between ones are doubled, multiplied by 2. Well, we already figured out earlier b minus a over n was 1. But anyway, if I plug it in again here, b minus a over 2n would be 6 over 12, which is 1/2. This is basically just the same thing as h over 2, right, from the trapezoid area formula. So I have that right here. So that's my b minus a over 2n, or my h over 2. And then I basically just added all of that up in my calculator to get this decimal, and then multiplied it by 1/2 or divided it by 2 to get this. So now what we should do is check that on our calculator using the rules we just learned. So we're going to use the Math 9 option. Oh, and by the way, if you want to do a cube root on your calculator, that would be Math 4. Math 4 offers the cube root feature to be able to plug that in your calculator. But when we do the definite integral on our calculator, it comes out to be about 8.177043309. This would be the exact value of the area under the curve, and here's our approximate value, which I can see was an underestimate, right? It is less than the actual value, and that is because the curve that I was finding the area under was concave down. This was a concave down curve, so the tops of my trapezoids came a little bit below, especially right here when I had like a triangle for that first one instead of the curve. They were basically undercutting the area and then finding an underestimate of it. Now, the last two examples are cases where you wouldn't necessarily be able to use the trapezoid rule. You'd have to just understand how the trapezoid rule came to be and basically just use areas of trapezoids, areas of different trapezoids. So these were both taken from AP tests where they like to kind of keep you on your toes. So let's take a look together at example 2. So example 2 is telling us that concert tickets went on sale at noon. So understand also that t equals 0 is representing noon, and we're sold out within 9 hours. The number of people waiting in line is modeled by this twice differentiable function L. So this is number of people waiting in line. And the values of this function are given at different times. So use a trapezoidal sum, okay, with 3 subintervals to estimate the average number. We'll figure out what additional thing we'll have to do to get the average. The average number of people waiting in line during the first 4 hours. This is another thing AP Test likes to do, is kind of throw you off by giving you extra information you don't need. We're going to block out everything that happened after 4 hours and only pay attention from 0 to 4. What we want to pay close attention to here is that there are 3 subintervals. So the first one would be between 0 and 1, which the change in time there, this is like my change in x, t is like my x, is just 1, between 0 to 1. The second trapezoid would be between 1 and 3. Now notice my change in time there is 2. That is the reason I won't be able to use the trapezoid rule, because I'm not going to have the same width of each trapezoid, so I'm not going to have the same h or the same b minus a over n, if you will. So I'm going to just have to do 3 different trapezoids to get this trapezoidal sum. My third trapezoid is going to be between these x values of 3 and 4, or my t values of 3 and 4, and the change in time there is 1. Okay, so basically what we're kind of doing is imagining, so let me just draw this picture of over here. It's going to be not to scale at all, but anyway, just to kind of give you an idea. So here's my time values of 0, 1, 3, and 4. And my number of people waiting in line, so I'm going to say like 120 is right here. I'm going to say 156 is up here. This is not to scale at all, but anyway, just to kind of give you an idea. Here's the 176. So my first trapezoid would have a base 1. So this is my L of 0, if you will, which will be base 1 of my first trapezoid. And this guy, the 156, is my L of 1. 176 is my L of 3. And 126 is my L of 4. So these are going to be the bases of my trapezoid. So I'll have one that goes all the way up to here, and then L of 1 is 156. So this is like my first trapezoid right here. So I'm going to find the area of that trapezoid. And then from 1 to 3, so I'm going all the way to here. At 3 I had a y value of 176. So then this would be like trapezoid number 2. We're going to find that area. And then from 3 to 4, 4 was down here at 126. So we'll put that like right there. This would be like my third trapezoid. So I'm going to find this area by simply using the area formula for a trapezoid and just sort of adding these all up. And what this is doing is give me an approximate value for the area under the graph of the number of people waiting in line. So it's kind of accumulating all of the people that waited in line over the accrued time from 0 to 4. Okay, so trapezoid number 1, we'll just call it T1, that's this guy right here. So we're going to do 1/2 base 1 plus base 2 times height. Height, if you remember, is your change in x or your change in time. So my height for that one is 1. That's my change in t. Base 1 would be L of 0, and base 2 would be L of 1. So trapezoid number 1 is 1/2 times 120 plus 156 times my height, right, which is laying along the x-axis, is 1 for that first interval. So then the area for trapezoid number 1 is 138. So then we're going to find the area of trapezoid number 2. So trapezoid number 2 goes between 1 and 3. So the height, if you will, of that trapezoid is 2. That's my change in time. So I'm going to do 1/2 base 1, which is L of 1, plus base 2, which is L of 3, times 2, which is the change in time, the quote height of that trapezoid. So that's 1/2 times 156 plus 176 times 2. So add that up and multiply by 2 and divide by 2, and I get 332. Then lastly, for trapezoid number 3, so that's the one between 3 and 4. That's this guy right here. So again, it's 1/2 base 1 plus base 2, so L of 3 plus L of 4 times the change in time, change in t, that horizontal distance, which is 1. So that equals 1/2 times 176 plus 126. And add that up and divide by 2, and you get 151. So to find the trapezoidal sum that this problem is asking us to find, I basically just have to take these areas of my 3 different trapezoids, 1, 2, and 3, and add them up. So for this one, my trapezoidal sum is 138 plus 332 plus 151, which is equal to 621. Okay, so this right here, what does this represent? So this is basically finding the total number of people in line ever from 0 to 4. This is like total people right here. Total number of people. It's not giving me the average number of people waiting in line, which is what this question was asking me to find. So this is just yet another tactic of the AP test, is to kind of throw in these curves. So pay attention to that. So what we found here was the total number of people that had waited in line over this 4-hour period. What I want to find is the average number of people waiting in line in the first 4 hours. So I just have to take this and divide it by the total time. So this is total number of people, this is total time, and what that will do is give me an average number of people in line at any given hour between those hours of 0 to 4. And so that would be, so my average number of people in line would be about 155.25. So there we go. So we used our trapezoid rule to approximate the total number of people that had been in line ever in the first 4 hours. Then I divided that by total time, which was 4 hours, to get an average number of people in line at any given time in the first 4 hours. Now, example 3 is a very similar style AP question. Again, they're giving us a table of values. So a lot of time when they ask you to use a trapezoid rule, which is what this did, ask you to find a trapezoidal sum with 4 subintervals, it'll give you a table of values instead of an equation. And here it says use the 4 subintervals given by the table. So they will also expect you to be able to look at how these x values are changing to decide the height of each of your trapezoids, which may not always be the same. So right here I can find my change in time again was 2, which is my height of the trapezoid. Here it's 3. Between 5 and 7 it's 2. Between 7 and 8 it's 1. So I have varying widths of varying distances between my time values, which means that each of my trapezoids are going to have varying widths, varying heights. So instead of using the formula for a trapezoidal sum like our book gives us, we're going to just think about what we're doing, which is finding the areas of 4 separate trapezoids and just adding them together. Now it says to do that, use that trapezoid sum to approximate the value of this integral right here. 1 over 8 times the integral from 0 to 8 of e of t dt. The trapezoid sum is only going to be able to find an approximate value for this definite integral. So the trapezoid sum is finding the value of the integral. What we're going to have to do after we find our trapezoid sum is then multiply it by 1 over 8. So that 1 over 8 is not determined with the trapezoid sum, only the integral is, so we'll have to multiply that at the end, and then also explain what this means. So let's first do the trapezoid sum. So notice I have 4 subintervals. This is interval number 1, interval number 2, interval number 3, interval number 4. This is my e of 0, e of 2, e of 5, e of 7, and e of 8. So these are all of my y values, or my bases, if you will. So for trapezoid number 1, I'm going to do 1/2 base 1 plus base 2 times height, right? But remember that height is always your horizontal change, the change between your x values, or in this case your t values. So in this case, that would equal 2 for my first trapezoid. So I have 1/2 0 plus 4 times 2, which is equal to 4. So that's the area of my first trapezoid. Then for my second trapezoid, that would be between 2 and 5. So it'd be 1/2 e of 2 plus e of 5, those are my 2 bases, times my change in time, which from 2 to 5 is 3. So that's 1/2 4 plus 13 times 3. And that is equal to 25.5. Then for my third trapezoid, that would be the one that's between 5 and 7. So I have 1/2 e of 5 plus e of 7 times the change between 5 and 7, which is 2. So then that would be 1/2 13 plus 21 times 2 equals 34. And then lastly, for the fourth trapezoid, the fourth trapezoid is the one between 7 and 8. So it's 1/2 e of 7 plus e of 8 times the difference between 7 and 8, which would be the height of that trapezoid, which is 1. And so that's 1/2 21 plus 23 times 1. And that's 22. So to find my trapezoidal sum, I add up the different trapezoid areas that I found. And remember, that trapezoid sum will give me the value of the integral part. So I add those up and I get 85.5. Now that's the value of the integral from 0 to 8 of e of t dt. But this then wants me to multiply that by 1/8, because it wants me to find the value of 1/8 times the integral. Okay, so what is that? That would be 10.6875. So that is giving me the value of 1 over 8 times the integral from 0 to 8 e of t dt. Then they want you to explain the meaning of that. Well, we haven't actually told you what this is yet. We're going to learn what this is. This is a formula for the average value of a function. This formula right here is finding the average value of e of t. It's the average value of whatever function is inside the integral. Because it's doing 1 over b minus a times the integral from a to b of e of t dt. So, and like I said, we're going to cover this formula in another section. But anyway, since we're doing this AP question right now, you can kind of see how they want you to describe what things mean. So this would represent the average number of, now remember, e of t was in hundreds of entries. So the average number of hundreds of entries for this, naming this new baby elephant, right? People put in their names. So this is the average number of hundreds of entries in the box in this little box where they dropped them off, between, because it was from 0 to 8, right? Between the hours of noon, right? Because t equals 0 represented noon. So this is referring to noon to 8 hours after noon, so 8 p.m. So that would be the meaning of that value that they were asking us to find with a trapezoid sum that we use to approximate the area under the curve. Okay, so you've seen how this rule works in a more abstract sense, and you've also seen now how we can use it in a more applied sense on the AP test. So I look forward to seeing you in class where we can try some of these together.